Dirac delta potential and bound states. What is this Dirac delta? First we will discuss about Dirac delta function, then we will discuss the bound state in a Dirac delta potential. So first of all, we have to know a little about Dirac delta function. The definition of Dirac delta potential is delta of x minus x0 is equal to 0 if x not equal to x0 and is equal to infinity if x equal to x0. So we can draw this function, that is, this is our x-axis and this is y-axis. See, this is the x minus x and this is plus x, and when x become x0, let us consider this point is x equal to x0, then the value of delta of x minus x0 is infinity, and when it is beyond that region, that is when it is here or anywhere in the positive x-axis or minus x-axis, its value is 0. That is, it is look like a spike. It goes to infinity. So this extends up to infinity. But there is an interesting property. The area under the curve of this delta function is equal to 1. Even it is extending up to infinity, the area under the curve is 1. That is a very interesting property, right? That is, if we are integrating this Dirac delta from minus infinity to infinity, that is integral delta of x minus x0 dx, then the value will be equal to 1. That is why I told you the area under the curve equal to 1. See, from this equation, we can find out the dimension of delta. What is that? That is dimension of delta into dimension of dx, that is, we know length, that is equal to 1. Therefore, the dimension of delta is equal to 1 by L, that is equal to L inverse. So this is the dimension of delta function, that is L inverse. And we can use the same analogy to find out the dimension of wave function. So let us consider this is first one. Now we are going to find out the dimension of a wave function. That is, we know the normalization condition is minus infinity to infinity mod psi square dx equal to 1. This is in the case of a 1D, right? Because only x is there. So this is a 1D case. That is 1D wave function. So the dimension of mod psi square into dimension of x, that is L, equal to 1. Therefore, the dimension of wave function psi in 1D case will be equal to 1 by L raised to half, that is equal to L raised to minus 1 by 2. This is for the 1D case. Okay. That is, if wave function is a one-dimensional one, then we get dimension of wave function psi is equal to L raised to minus half. Then what will be the dimension of a wave function in 2D case? That is 2D wave function. That is dimension of psi, where psi is a function of x and y, right? So that will be equal to L raised to minus 2 by 2. That is equal to L raised to minus 1. And for 3D case, the dimension of 3D wave function, that is, this psi is a function of x, y and z. So when we are integrating, we have to take dx, dy, dz. So dimension of each of this is L into L into L. Okay. So this one we will get as L raised to minus 3 by 2. So these are the dimension of wave function in 1D case, 2D case and the 3D case. Let us consider one example problem. Here a wave function is given. that is psi is equal to a into delta x minus x0, and the question is to find the dimension of a. That is, we have to take the dimension of psi is equal to dimension of a into dimension of delta of x minus x0. Here we know this wave function is in one dimensional wave function because delta is a function of x only. Okay, so for a 1D wave function, the dimension will be L raised to minus half. That is equal to dimension of a into dimension of delta function, that is L raised to minus 1. So from this equation, just by rearranging, we can find out the dimension of a, that is equal to L raised to minus half by L raised to minus 1, that is equal to L raised to half. And this one is a work for you. Nothing is there. See, this is a wave function is a function of x only. So this is a 1D wave function, right? And you know the dimension of 1D wave function. And you can find out the dimension of x square into x minus 2 function. Then you can easily solve the value for I. Please do this by yourself. The answer will be I is equal to 7 by 2. So please solve this and reach to the answer I equal to 7 by 2. Now you are familiar with this Dirac delta function. And now we are going again to our topic, that is Dirac delta potential and bound states. See, first we discussed about 1D box, right? So in a 1D box, we discussed a 1D box with a infinite potential. So this particle is trapped inside this box. It can't escape from this box, right? And we solved for the Schrodinger equation and we got a wave function for this 1D box and we got an energy for this 1D box. Okay. Similarly, here we are going to find out the wave function and energy of a particle which is trapped in a Dirac delta potential. From the definition of Dirac delta function, we know the graph will look like this one. See, this function goes up to infinity, but the area under this curve is equal to 1. Okay, now we are going to discuss about a particle which is trapped inside this potential. But if this is the Dirac delta potential, then how we can trap the particle? So we can invert this Dirac delta potential, that is like this one. So this is now our Dirac delta potential, that is minus delta of x. We inverted this Dirac delta potential. Okay, so this position is 0. So this is negative axis and this is positive axis. So here this infinity is the potential v of x, and here this delta of x is the potential v of x. Now in this potential, negative potential, a particle can be trapped. So there is a bound state. So our target is to find out the wave function psi and energy E of this particle trapped in a Dirac delta potential. So we have to solve the Schrodinger equation, that is H psi is equal to E psi. When solving this Schrodinger equation, we get a psi value, and the psi value will be corresponds to two states. One is bound state and one is scatter state. What is the bound state? Bound state is look like this one. So the particle is bounded to that region. It can escape from that potential well. Why? Because energy of the particle is less than the potential of the potential well. See, the potential of potential well is infinity. So the particle can't jump this infinite potential and come out of this potential well. That is why we are telling it is a bound particle. And what is a scattered state? Scattered state is a situation where energy of the particle is greater than potential well. To understand this idea, I tell you some real life things. That is, if you are in a well. See, you are here. So you have some energy, and if you are trying to come out of this well, you will try to jump, and when jumping, you will reach maximum up to this energy level. That is, the maximum energy of you is up to this much. But see, the potential energy is here. This is the potential energy, and this is your energy. So here, your energy is less than potential energy. So you can escape from this well. You will be bounded there. But if the case is like this one, if the depth of the well is very less, and this is you. Okay, so this is the potential of the well. Okay, and you are very energetic person, and you can definitely jump over this well, right? That is, your energy is this one. That is, your energy is greater than the potential well. So you are not bounded to that potential well. Okay, so your state is a scattered state. This is the idea of bound state and scattered state. Here this Dirac delta potential is infinite potential. So the particle will be in a bound state. Okay, so we are going to discuss only this part. That is bound state wave function of a particle in a Dirac delta potential and its energy. Now let us consider the Dirac delta potential V of x equal to a delta of x. Here I am taking this as a negative Dirac delta potential, that is, it is an attractive potential. That is, see, this Dirac delta function is inverted. So the graph will look like this one. Okay, inverted, right? And this is V of x, and V of x equal to minus a delta of x, and this axis is x axis. And when x value is equal to 0, see, when x value equal to 0, the value of Dirac delta potential is minus infinity. And for a particle to be in bound state, the condition is, bound state condition is, E should be less than V. Here you see, the potential is a negative function. So energy should also have a negative value. Okay, so the particle will be in this position. See, the energy, this is the energy of the particle, right? So the energy of the particle is also in the negative axis. See, okay, so the energy is also negative. Then only it will be in a bound state. And we know the definition of Dirac delta function, that is, delta of x minus x0 is equal to 0 if x is not equal to x0 and it is equal to infinity if x equal to x0. That is, this point is x0. Okay, when x equal to x0, the value is infinity, right? And there is one more condition. If you are integrating a Dirac delta function from a to b, that is f of x into delta of x minus x0 dx is equal to f of x0 if this x0 is in between this a and b. Now we are going to find out the corresponding wave function psi for this particle. So this particle is in a potential, that is v of x is equal to minus a delta of x. And we know the Schrodinger equation is h psi is equal to E psi. And we can expand this Schrodinger equation, that is del square psi plus 2m by h cross square E minus v into psi equal to 0. Now I can expand this equation, that is del square psi plus 2m by h cross square E minus 2m v by h cross square into psi equal to 0. Here we know the value of potential, that is minus a delta of x. So this will be equal to del square psi plus 2m by h cross square E into psi minus into minus, that is plus 2m a delta of x by h cross square psi equal to 0. Here I told you, for this particle to be in a bound state, the energy E should be negative. So we can rewrite this Schrodinger equation as follows, that is del square psi minus 2m E by h cross square psi plus 2m a into delta of x by h cross square psi equal to 0. We know the value of delta of x at two conditions, that is one is at x equal to 0, this delta of x will be equal to infinity. So we can't solve this equation by substituting x equal to 0 in this condition. So we can solve this Schrodinger equation at x equal to 0 because this function become infinity. So this is impossible to solve. Then what we do? We take the next condition, that is when x is not equal to 0, we know delta of x is equal to 0. So that is a finite condition and we can substitute this condition in this equation. So we will get del square psi minus 2m e by h cross square into psi is equal to 0. Where we can call this entire term as some k square. That is, this is equal to del square psi minus k square psi equal to 0. So this is in the form of a differential equation, that is d square minus k square equal to 0. That is, the solution of this differential equation will be equal to plus or minus k. This is the real values. So for real values, the solution, that is psi, will be equal to, there will be two solutions, that is one is e raised to kx and one is e raised to minus kx, where this e raised to kx solution we obtain for x less than 0 and this one will obtain for x greater than 0. And why this wave function is different in different region? I tell you the reason. Here this is our potential, direct delta potential, this is a negative potential. Okay, and goes to minus infinity, right? So our particle is here in between this region, so it has certain energy. Okay, and there will be a wave function inside this region, and outside this region the wave function will decay exponentially. So for the positive x-axis, that is x is greater than 0 e raised to minus kx, it will be exponentially decreases only when this function is minus kx. Okay, and in the negative x region, see, e raised to kx, so automatically the x value in this negative region is minus, so e raised to minus kx, so it will decay here. That is the wave function corresponds to particle will be 0 other than the region where the particle is existing. So here this is the region where the particle is existing. So beyond that region the wave function should vanish. That is why the wave function is like this one. Okay. Now to find out the exact wave function, you have to substitute the boundary conditions and solve for it. So when we are substituting this boundary condition and doing the mathematical manipulations, finally we will get a value for k that will equal to ma by h cross square. And when substituting this k value in the above expression, we get psi is equal to e raised to ma by h square x in the region x less than 0 and e raised to minus ma by h cross square into x in the region x greater than 0. Now we can summarize all these ideas. That is, if the particle is in a Dirac delta potential, that is V of x is equal to minus a delta of x, then we will get a k value that is equal to ma by h cross square, and we will get a wave function psi of x that is equal to e raised to minus ma by h square modulus of x. That is, in the negative region x will have a negative value, and in the positive region x will have a positive value. Now we want to find out the energy of particle in the Dirac delta potential. We got the wave function, so the particle in that wave function will have certain energy. And what will be the energy? We know this k value, that is k is equal to m a by h cross square, and we know the energy equation E is equal to p square by 2m, where p is equal to h cut k, that is h square k square by 2m. That is, E is equal to h cut square by 2m into k square. K square is equal to m square a square by h cut square into square. So we can cancel this h cut square and this square, and m square and m. So finally we get energy E equal to m a square by 2 h cut square. And here the particle is in a negative potential, and for a particle to be in a bound state, the energy should be negative. So this is minus. So this is the energy of the particle which is bounded in a Dirac delta potential. Okay. Step potential. Earlier we discussed about infinite potentials. That is, for 1D box we took the potential walls extend up to infinity, and in the case of a Dirac delta potential, the potential is also infinite potential, that is like this one. Okay, so this tends to up to infinity. Right, so these are the infinite potential. Now we are going to discuss about step potential, that is finite potential. That is, this step potential will look like this one. This is V of x, and this is the step potential. That is, this have a certain potential, that is V. So here there are two regions. Suppose this is x equal to 0, then this is region 1 and this is region 2. In the region 1, potential V is equal to 0, and in the region 2, the potential is V. Here we can consider two cases of step potential. The first case is energy of the particle is greater than potential energy of the barrier or step, and case 2 is energy of the particle is less than the potential barrier or the step. Okay, so first we are going to discuss the case 1, then we will discuss the case 2. Case 1, that is energy of the particle is greater than potential of the barrier. That is, we can draw the diagram. So this is V of x and this is x equal to 0, and the step is this one, and the potential of the step is V, and here this potential is equal to 0. And this is region 1 and this is region 2. And the particle have an energy which is greater than potential energy, that is, this will be the energy of the particle. This is similar to a real life case, that is, there is a step and this is u. Okay, see, this is the potential V and you have sufficient energy to jump over this step. So you can jump over this step, that is, your energy is definitely greater than potential of the step. Okay, this is the case. Now we can come back to our problem. So the problem is to find out the wave function of such a particle. So to find out the wave function, we have to solve Schrodinger equation. And what is the Schrodinger equation? That is del square psi plus 2m e minus v into psi by h square is equal to 0. Here we know del square is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. But here this is a 1D case, only x-axis is there, so all this term will be equal to 0. The Schrodinger equation will reduce us to dou square psi by dou x square plus 2m by h square e minus v into psi equal to 0. Now we can solve this Schrodinger equation in region 1. So we get the wave function of the particle in the region 1. Okay, so in the region 1, potential V is equal to 0. That is, we have to substitute this value of V in the Schrodinger equation. So we will get dou square psi by dou x square plus 2m e by h square into psi equal to 0. Here this one is k1 square because it is in the region 1, so I am calling this as k1 square. So this is a second order differential equation in the form of d square plus k1 square equal to 0. So the solution will be d will be equal to plus or minus ik. Therefore the solution, that is wave function, here the wave function is in the region 1, so I am calling it as psi 1 will be equal to a e raised to ikx plus b e raised to minus ikx. Now we can check the wave function for region 2. In the region 2, the potential V is equal to V. Okay, so the Schrodinger equation is dou square psi by dou x square plus 2m by h square e minus v into psi equal to 0. Here this entire term I am calling as k2 square because it is in the region 2. And you can see the energy is greater than potential, so this is a positive one. So this is d square plus k2 square equal to 0. So again we will get a value for d, that is equal to plus or minus I k2. Here it is k1. Okay, k1. We will get wave function in this region 2, that is psi 2 equal to c e raised to I k2 x plus d e raised to minus I k2 x. Here this is our step potential. Here the potential is V in the region 2 and this is x equal to 0, and this is called region 1, and this is region 2. Now, in the region 1, we got the wave function psi1 is equal to a e raised to ik1x plus b e raised to minus ik1x. Here, see, e raised to plus ik1x. This wave is traveling in the positive x direction. So, we get a wave which is traveling in the positive x direction, that is the incident wave, that is a e raised to ik1x. Now, the second type, that is b e raised to minus ik1x. So, this wave is traveling in the opposite direction in the region 1, that is the reflected wave. That is b e raised to minus ik1x. Now, in the region 2, this is the wave function. So, here also one wave is in the forward x direction, that is c e raised to ik2x, and there is another wave which is traveling in the negative x direction, that is d e raised to minus ik2x. Here in the region 1, one wave is incident wave and one is reflected wave. And this is a physically possible situation, because here at the boundary at x equal to 0, the potential is changing, so there will be a chance of reflected wave. But in the region 2, one wave is traveling in the forward direction and one wave is traveling in the negative direction. But here there is no difference in the potential, therefore there will be no reflection. Therefore, this wave will not exist. We will get some mathematical solution, but that mathematical solution will not always represent the physical reality. So, in physical reality, there will not be any reflection. So, that time is equal to 0. So, the physically valid wave function will be psi1 will be equal to a e raised to ik1x plus b e raised to minus ik1x, and psi2 is equal to, there is no reflected wave, only forward wave, that is c e raised to ik2x. So these are the wave functions a and b for the particle in the region 1 and region 2. Here we got the wave function in region 1 and the region 2. In region 1, we got psi1 is equal to a e raised to ik1x plus b e raised to minus ik1x, and in the region 2, we got wave function psi2 is equal to c e raised to ik2x. So this is equation 1 and this is equation 2. Now we want to evaluate this constant a, b and c. How we can find out? We have to use the finite potential boundary conditions. What is this finite potential boundary condition? The finite potential boundary condition will be a continuous boundary. That means in the earlier case, in the case of a 1D box or something, see, the potential is infinity. So wave function will exist only inside this box. There is no chance of finding the particle outside the box, here or here. But now the boundary condition is finite potential boundary condition. So like this one. Okay, so if the particle is in this box, then there will be a chance of being found the particle outside the box also. That is at the boundary. See, here there is a wave function and here there is no wave function. But in this case, inside the potential well, there is a wave function, and outside the potential, there is also a wave function. They are different, but at this boundary point, they will have same value and their slope also will be same. So this is the condition of a continuous boundary. Okay. Thus, the first boundary condition is psi 1 at x equal to 0 will be equal to psi 2 at x equal to 0. At the boundary, their value will be same. That is, we have to substitute this value of x equal to 0 in psi 1 and psi 2. So what we get? We get psi 1. When we are substituting x equal to 0, it will become a plus b equal to c. Now, we are using the second boundary condition. What is second boundary condition? Slope is same, that is dou psi 1 by dou x at x equal to 0 will be equal to dou psi 2 by dou x at x equal to 0. So we have to take the partial derivative of this psi 1 and psi 2. So partial derivative of psi 1 will give a e raised to I k1x into derivative of I k1x, that is I k1, plus b e raised to minus I k1x into minus I k1 is equal to derivative of psi 2, that is c e raised to I k2 x into I k2. So we have to evaluate or substitute x equal to 0 here, and here also we have to substitute x equal to 0. So we get a I k1 plus b into minus I k1 is equal to c into I k2. That is k1 into a minus b is equal to k2 into c. That is a minus b is equal to k2 by k1 into c. So from these two equations, we can do the mathematical manipulations and we can find out the values of a, b and c. First I am going to add the equation a with the equation b. So what we will get? That is 2a equal to c plus k2 by k1c. That is 2a is equal to c into k1 plus k2 by k1. And similarly, I am subtracting equation b from a. So I will get 2b is equal to c minus k2 by k1 into c. Therefore, we get 2b is equal to c into k1 minus k2 by k1. That is, here a is equal to c k1 plus k2 by 2k1 and b is equal to c into k1 minus k2 by 2k1. Now I want to evaluate three parameters. One is c by a, another is c by b, and third one is b by a. What will be the value of these three times? First one, c by a, that we will get as 2k1 by k1 plus k2, and next one is c by b, so that one we will get as 2k1 by k1 minus k2, and from this above two equations we can find out p by a, that will be equal to k1 minus k2 by k1 plus k2. So by substituting these constants in the wave function, we will get the exact solution of particle in a step well. Probability current density. See, here we are discussing about a step potential. So it is like this one. This is the potential V of x, and this is the step potential, that is this V. So when a particle of energy E, which is greater than potential of step, then when we solving the Schrodinger equation, we will get wave function in the region 1, that is one is incident wave and the corresponding wave function will be a e raised to I k1x, and there will be a reflected wave, and corresponding wave function will be b e raised to minus I k1x, and in the region 2 there will be a transmitted wave, and its wave function is c e raised to I k2x. See, this is x equal to 0. Okay. So this one is incident wave function, and this one is reflected wave function, and this one is transmitted wave function. That is, incident wave function is equal to a e raised to I k1x. Now I want to find out the probability current density. That is Ji, probability current density of incident wave. Earlier we discussed how we can find out the probability current density. That is h cut k. Here k is k1 by m into modulus of amplitude square. That is velocity into modulus of amplitude square. Okay, that is h cut k is p by m is v, right? And earlier we discussed this idea and solved many problems. So this is the modulus of Ji, that is probability current density of incident wave. Similarly, we can find out the probability current density for reflected wave. Psi r, that is its wave function is b e raised to minus I k1x, and the probability current density of this reflected wave is Jr, and that is equal to h cut k case. This is minus k, that is minus h cut k by m into modulus of b square. But we are interested in the magnitude of probability current density, that is modulus of Jr. So the sign is not important. Okay. Here the minus sign represents the wave is traveling in the negative direction. That is why it have a negative velocity. That is, this term represents velocity, right? But here we are interested only in its magnitude. And the third one, psi t, that is transmitted wave function is c e raised to I k2x, and here we can find out the probability current density Jt, that is equal to h cut k by m into mod c square. So these are the probability current density of incident wave, reflected wave, and transmitted wave in the case of a step potential. Reflection and transmission coefficient. So we evaluated the probability current density. So we got for incident wave, the probability current density is equal to h cut k1 by m modulus of a square, and for reflected wave, the probability current density is equal to h cut k1 by m into mod b square, and for transmitted wave, probability current density J transmitted is equal to h cut k2 by m mod c square. So from these equations, we can find out the reflection coefficient and the transmission coefficient. That is, reflection coefficient is R. R is defined as J reflection by J incident. That is, it is a ratio of probability current density. One is probability current density of reflected wave by probability current density of incident wave. That is equal to mod b square by mod a square. So that is equal to, earlier we found out the values of b by a, that is equal to k1 minus k2 by k1 plus k2 all square. Now second one, we can find out the transmission coefficient. That is T, that is transmission coefficient is defined as J transmission by J incident equal to, what is J transmitted? This one, that is H cut K2 by M into mod C square divided by J incident, that is this one, that is H cut K1 by M mod A square. So here H cut by M are common terms, so it will cancels. So we get K2 mod C square by K1 mod A square. And earlier we found out the value of C by A. So substitute the value of C by A. So we can find out the transmission coefficient T is equal to K2 by K1 into 4 K1 square by K1 plus K2 all square. That is, we will get transmission coefficient T is equal to 4 into K1 K2 by K1 plus K2 all square. Therefore, for a step potential and the particle energy E is greater than potential of the step, then the reflection coefficient will be equal to K1 minus K2 by K1 plus K2 all square, and the transmission coefficient will be equal to 4 K1 K2 by K1 plus K2 all square. Here when we are deriving this equation, we took K1 as root 2m E by H cut square, and we took K2 as root 2m E minus V by H cut square. So when we are solving the Schrodinger equation, we substituted 2me by H cut square as K1 square and 2m into E minus V by H cut square as K2 square. Are you remembering? After substitution of this one only, we solved the differential equation, second order differential equation. Okay, so now we are again resubstituting this value of K1 and K2. So we can find out the reflection coefficient in terms of energy. That is, we have to substitute this value of K1 and K2 here. So we will get R equal to root of E minus root of E minus V all square by root of E plus root of E minus V all square. And similarly, if you are substituting this value of K1, K2 and K1 plus K2, you will get transmission coefficient T in terms of energy, that is 4 root E into root E minus V by root E plus root E minus V all square. So these are very important equations. One example problem. There is a step potential and the height of the potential is 30 electron volt, that is its energy. Okay, and the particle have certain energy, that is E equal to 40 eV. So this is potential V, that is equal to 30 eV, and the energy of the particle is 40 eV. Now we have to find out reflection coefficient and transmission coefficient. So first we have to find out the reflection coefficient. So we have to substitute this energy in this expression. So root E, that is the energy of the particle, that is root 40 minus root E minus V, that is E is 40 minus 30, that is root 10 all square divided by root 40 plus root 10 all square. So we will get r is equal to, we have to take the square of this term, that is 40 minus 2 root 40 into root 10 plus 10 by 40 plus 2 root 40 root 10 plus 10. So what will be the value? That is equal to 40 in minus 40 plus 10 by 40 plus 40 plus 10. That is, we got 10 by 90, that is 1 by 9. Now we have to evaluate this t value, transmission coefficient, that is 4 into root e. Root e is 40 into root e minus v is 10 by, see, we already evaluated the denominator value, that is 90. So what we will get, that is equal to 4 into root of, say, 400 by 90. That is, we can write 4 into root 4 into 100 by 90. Okay, so it is, we can easily find out the root of 400. That is 4 into 2 into 10 by 90. That is 80 by 90. That is equal to 8 by 9. So this is the transmission coefficient. Here you can see, when we are adding reflection coefficient and transmission coefficient, we will get it is equal to 1. That is, t plus r is equal to 1. So once you got the reflection coefficient, then you can easily find out the transmission coefficient and vice versa. Okay. Reflection and transmission coefficient. So we evaluated the probability current density. So we got, for incident wave, the probability current density is equal to h hat k1 by m modulus of a square, and for reflected wave, the probability current density is equal to h hat k1 by m into mod b square, and for transmitted wave, probability current density J transmitted is equal to h hat k2 by m mod c square. So from these equations, we can find out the reflection coefficient and the transmission coefficient. That is, reflection coefficient is R. R is defined as J reflection by J incident. That is, it is a ratio of probability current density. One is probability current density of reflected wave by probability current density of incident wave. That is equal to mod b square by mod a square. So that is equal to, earlier we found out the values of b by a, that is equal to k1 minus k2 by k1 plus k2 all square. Now second one, we can find out the transmission coefficient. That is T, that is, transmission coefficient is defined as J transmission by J incident equal to, what is J transmitted? This one, that is h hat k2 by m into mod c square divided by J incident, that is this one, that is h hat k1 by m mod a square. So here h hat by m are common terms, so it will cancels. So we get k2 mod c square by k1 mod a square. And earlier we found out the value of c by a. So substitute the value of c by a. So we can find out the transmission coefficient T is equal to K2 by K1 into 4 K1 square by K1 plus K2 all square. That is, we will get transmission coefficient T is equal to 4 into K1 K2 by K1 plus K2 all square. Therefore, for a step potential and the particle energy E is greater than potential of the step, then the reflection coefficient will be equal to K1 minus K2 by K1 plus K2 all square, and the transmission coefficient will be equal to 4 K1 K2 by K1 plus K2 all square. Here, when we are deriving this equation, we took K1 as root 2m E by h cut square, and we took K2 as root 2m E minus V by h cut square. So when we are solving the Schrodinger equation, we substituted 2me by h cut square as K1 square and 2m into E minus V by h cut square as K2 square. Are you remembering? After substitution of this one only, we solved the differential equation, second order differential equation. Okay, so now we are again resubstituting this value of K1 and K2. So we can find out the reflection coefficient in terms of energy. That is, we have to substitute this value of K1 and K2 here. So we will get R equal to root of E minus root of E minus V all square by root of E plus root of E minus V all square. And similarly, if you are substituting this value of K1, K2 and K1 plus K2, you will get transmission coefficient T in terms of energy, that is 4 root E into root E minus V by root E plus root E minus V all square. So these are very important equations. One example problem. There is a step potential and the height of the potential is 30 electron volt, that is its energy. Okay, and the particle have certain energy, that is E equal to 40 eV. So this is potential V, that is equal to 30 eV, and the energy of the particle is 40 eV. Now we have to find out reflection coefficient and transmission coefficient. So first we have to find out the reflection coefficient. So we have to substitute this energy in this expression. So root E, that is the energy of the particle, that is root 40 minus root E minus V, that is E is 40 minus 30, that is root 10 all square divided by root 40 plus root 10 all square. So we will get R is equal to, we have to take the square of this term, that is 40 minus 2 root 40 into root 10 plus 10 by 40 plus 2 root 40 root 10 plus 10. So what will be the value? That is equal to 40 in minus 40 plus 10 by 40 plus 40 plus 10. That is, we got 10 by 90, that is 1 by 9. Now we have to evaluate this T value, transmission coefficient, that is 4 into root E. Root E is 40 into root E minus V is 10 by, see, we already evaluated the denominator value, that is 90. So what we will get? that is equal to 4 into root of say 400 by 90. That is, we can write 4 into root 4 into 100 by 90. Okay, so it is, we can easily find out the root of 400. That is 4 into 2 into 10 by 90. That is 80 by 90. That is equal to 8 by 9. So this is the transmission coefficient. Here you can see when we are adding reflection coefficient and transmission coefficient, we will get it is equal to 1. That is T plus R is equal to 1. So once you got the reflection coefficient, then you can easily find out the transmission coefficient and vice versa. Okay. An important note. See, here we are discussing about step potential and energy of the particle is greater than potential energy. Okay. So we got wave function into region. So this is the potential V. And this is region 1 and this is region 2. And the wave function in the region 2 and region 1 we know, that is in region 1 there is a forward travelling wave that is equal to a e raised to I k1x and a backward travelling wave that is b e raised to minus I k1x, and in region 2 a forward travelling wave is there, that is c e raised to I k2x. That is, in the region 1 the total wave function psi is a linear combination of psi 1 and psi 2. Therefore, if you are finding mod psi square, that is, you know, you have to take conjugate of these terms, that is psi 1 star plus psi 2 star into psi 1 plus psi 2. So when we are substituting this psi 1 values here and when finding the solution for mod psi square, so in the region 1 you will obtain mod psi square is equal to some constant a square psi 1 square plus b square psi 2 square plus 2ab psi 1 psi 2. And here this psi 1 and psi 2 consist of I times, that is psi 1 is equal to a e raised to I k1x and psi 2 is equal to b e raised to minus I k1x. Here the values e raised to I k1x and e raised to minus I k1x are oscillatory in nature. And here, what is this mod psi square? That is probability density. Therefore, the probability density have a oscillatory nature in the region 1. And now we can check the region 2. In region 2, the wave function is psi3, that is equal to c e raised to I k2x. Now we can find out the mod psi3 value, that is probability density, that is we get psi3 star psi3, that is equal to c e raised to minus I k2x into c e raised to I k2x. So mod psi3 square is equal to, sorry, here it is square, okay, square is equal to c square, that is a constant value. Okay, so in the region 2, the wave function, the probability density of wave function is constant, and in the region 1, the probability density is a oscillatory one. That is, if we draw a graph of probability density in both region, that is, this is region 1 and this is region 2, where this represents the mod square, that is the probability density. So in the region 2, it will have a constant value, and in region 1, it will have a oscillatory nature. So the probability density in region 1 and region 2 will look like this one. This is for a step potential where energy of the particle is greater than potential. Now let us consider another case of step potential, that is energy of the particle is less than the potential. That is, the graph will look like this one. And see, this is the potential barrier. And right now, the energy of the particle is less than potential barrier. So this is the energy of the particle. And this position is x equal to 0. Okay, and I'm calling this is region 1 and this is region 2. So again, we have to evaluate the wave function psi of the particle. To evaluate the wave function in region 1 and region 2, we need Schrodinger equation, that is dou square psi by dou x square plus 2m e minus v by h square into psi is equal to 0. So in the region 1, we now potential V is equal to 0. Therefore, the Schrodinger equation become dou square psi by dou x square plus 2m e by h square psi is equal to 0. So I can call this term as k1 square because it is in the region 1. So I am naming it as k1. So this is k1 square. So this is a differential equation, d square plus k1 square equal to 0. And the solution of this differential equation is d equal to plus or minus I k1. So the solution of Schrodinger equation in the region 1 is equal to a e raised to I k1x plus b e raised to minus I k1x. Now we have to evaluate the Schrodinger equation in region 2. In region 2, there is a potential V, and this potential V is greater than energy of the particle. So when we are substituting the Schrodinger equation, we get dou square psi by dou x square plus 2m by h square into e minus v psi is equal to 0. Here e minus v is less than v, therefore e minus v will be negative. Therefore I can rearrange this equation, Schrodinger equation, that is dou square psi by dou x square minus 2m by h cross square into v minus e into psi equal to 0. Now this entire term I am calling as k2 square. So this is a second order differential equation, that is d square minus k2 square equal to 0. That is, the solution of this differential is plus or minus k2. So the wave function psi in the region 2 will be equal to c e raised to k2x plus d e raised to minus k2x. Here we got the wave function in region 1 and 2. That is, this is our step potential of potential V, and the energy of the particle is less than the potential. Okay, so there is a incident wave. From the first solution, we got a wave which is traveling in the forward direction. That is the incident wave. And we got that is equal to a e raised to I k1x, and there is a reflected wave, that is b e raised to minus I k1x. So this is the region 1. And in the region 2, we got this solution. Okay, so the forward traveling wave, as x value increases, its value increases exponentially. So if this is the forward traveling wave, then its value increases exponentially. That is, this is c raised to k2x. And there is another wave, and for that one, as x value increases, its magnitude exponentially decreases. That is d raised to minus k2x. Here you see the amplitude of wave is increasing in the region 2 for the first case. So this is not a physically valid wave function. So only this one is the physically reliable solution in region 2. Therefore, we got wave function psi 1, that is the wave function in the region 1 is equal to a e raised to I k1x plus b e raised to minus I k1x, and in the region 2 we got psi 2 is equal to d e raised to minus k2x. And this is a wave function in region 1 and region 2 of a finite step potential. Okay. And this is a finite potential, so there will be a continuity of wave function in region 1 and region 2. That is, at this position, that is x equal to 0, the value of psi 1 and the value of psi 2 will be same, and the slope at this position also will be same. That is two boundary conditions. And this boundary is a continuous boundary. Therefore, first condition is psi 1 at x equal to 0 will be equal to psi 2 at x equal to 0. That is a e raised to I k1x plus b e raised to minus I k1x at x equal to 0 will be equal to psi 2, that is d e raised to minus k2x at x equal to 0. That is, we get a plus b equal to d. Now we can use the second boundary condition, that is slope will be same, that is dou psi 1 by dou x at x equal to 0 will be equal to dou psi 2 by dou x at x equal to 0. That is a e raised to I k1x into I k1 plus b e raised to minus I k1x into minus I k1 at x equal to 0 is equal to dou psi 2 by dou x, that is d e raised to minus k2x into minus k2 at x equal to 0. So substitute this value of x equal to 0 in this equation. So we will get a I k1 minus b I k1 equal to minus d k2. That is I k1 into a minus b is equal to minus d k2. Therefore, a minus b is equal to minus d k2 by I k1. That is, we can again rearrange, that is a minus b equal to I d k2 by k1. This is equation b. That is, we got a plus b is equal to d, and we got a minus b is equal to I k2 d by k1. Now we can add this equation a with the equation b. So we will get 2a is equal to d plus I k2 by k1 into d. That is 2a equal to d into 1 plus I k2 by k1. Once again, we can rearrange this equation. So we will get a equal to k1 plus I k2 by k1 into d. And this 2 will come down. That is k1 plus I k2 by 2 k1 into d. So let us call this as 1. And now I am going to subtract equation b from equation a. So what we will get? We will get 2b equal to d minus I k1 by k2 into d. That is equal to 2b is equal to d into 1 minus I k2 by k1. That is b is equal to k1 minus I k2 by 2 k1 into d. I am calling this as 2. Here from these equations we can find d by a, d by b and b by a. What is d by a? That is 2 k1 by k1 plus I k2. And what is d by b? That is, from this equation we can find out, right? That is d by b will be equal to 2 k1 by k1 minus I k2. And what is b by a? That is, we have to divide this equation by this one. So we will get k1 minus I k2 by k1 plus k2 I k2. Now we are going to find out reflection and transmission coefficient using these values. Probability current density and reflection and transmission coefficients. Now first we are going to find out the probability current density. That is, we know this is our case, that is step potential. This is potential V, and the energy of the particle is less than V. Now we have two waves in the region 1, that is incident wave psi 1, and it is equal to a e raised to I k1 x, and this is a reflected wave, that is psi r. So this is psi I incident wave, and this is psi reflected wave, that is equal to b e raised to minus I k1 x. And in the region 2 there is a wave, okay, it is decays to 0 value, and its wave function is d e raised to minus k2 x. That is, the incident wave function is equal to a e raised to I k1 x. Now we have to find out the probability current density J, that is equal to velocity into modulus of amplitude square. So the velocity is h cut, here k is k1 by m into modulus of a square. And here we are taking only the magnitude of probability current density, not the direction. Okay, so second one is reflected wave, that is psi r is equal to b e raised to minus I k1x. Now we have to find out the probability current density J R, that is equal to h cut k, here k is k1 by m into amplitude square, that is b square. But here you can see the k1 is minus k1, but here we are interested only in its magnitude. So it is plus. Okay. And third one, that is psi transmitted is equal to b e raised to minus k2x. See, this function is exponentially decreasing as x increases. Therefore, this function is not representing a traveling wave, because as this wave travels a little distance in the x direction, it will decays. Okay, so the probability current density for this wave is equal to 0. That is, this wave is not a traveling wave. Now we can find out the reflection coefficient. That is how much of the total wave is reflected. That is R equal to J reflected by J incident. Here this is J incident, and that is we got h cut k1 by m into modulus of b square divided by J incident, that is this one, that is h cut k1 by m mod a square, that is modulus of b by a all square. Just before we evaluated the value of b by a, therefore R is equal to k1 minus I k2 by k1 plus I k2 modulus square. And if you are evaluating this mod square of this complex function, you will get a value is equal to 1. Now we can find out the transmission coefficient. That is T is equal to J transmitted by J incident. What is J transmitted? We got its value equal to 0. So 0 by J incident, that is equal to 0. Earlier I told you one condition, that is reflection coefficient plus transmission coefficient is equal to 1. So if we got reflection coefficient, then by using this equation we can find out the transmission coefficient. Okay. Here why this transmission coefficient is 0? We know the potential is like this one. See, the particle energy is this much only. Okay, so this particle can't travel in this region. It is forbidden to access this region. Okay, that is why the transmission coefficient is equal to 0 when energy of the particle is less than potential. And this is like a real life situation, like there is a big wall. So you are only this much. You can never jump over this wall, right? So you are unable to access this region. Okay, because your energy, this is the potential of the wall and this is the your energy. Your energy is less than potential of the wall. So you can't overcome this potential barrier. That is, if you are running at high speed in this direction, you will collide with the wall and you will be reflected. That is, your reflection coefficient R equal to 1 and your transmission coefficient will be equal to 0. Okay, I think you got the idea. This is the same case when a particle is approaching a step potential whose potential is very much higher than the energy of the particle. Quantum tunneling. So we are discussing about step potential, right? So in the last case we discussed a step potential where energy of the particle is less than potential barrier. And we know the wave function in both the region. So this is the V of x and this is the potential V. And the particle have a energy which is less than energy of the potential barrier. So in the region 1, we got two wave functions. One is corresponds to incident wave and one is corresponds to reflected wave. And in the region 2, we got a wave function. It is look like this one. That is psi transmitted we obtained as d e raised to minus k2x. See, this is an exponential function, that is exponentially decreasing function. Okay, and we obtained the values of reflection coefficient, that is equal to 1, and transmission coefficient equal to 0. That is, whatever the incident wave, it is reflected back. That is why there is no transmission of the wave. That means the region from x equal to 0 to x equal to plus infinity, that region is inaccessible to the particle, right? Here we are discussing quantum mechanics, right? So in quantum mechanics there will be some different things will happen. Let us check what is the interesting thing happening here. So we are interested in the region 2. So in the region 2, we know the wave function, that is psi is equal to d e raised to minus k2x. Now we can find out the probability density, that is mod psi square, that is psi star psi, right? So when we are finding the psi star psi, here there is no I times, so we get this is equal to d into e raised to minus 2k2x. Now we want to find out the probability from region x equal to 0 to x equal to infinity. That is, now we are going to find out, is there any probability of finding the particle in the region x equal to 0 to x equal to infinity. Classically, that is, we discussed some real life experiences. In that experience, if there is a big wall in front of you, then you are unable to access the region beyond that wall. That is, the probability of finding you in the region beyond that wall is 0. Okay, there is no probability to access that region for you. And we can just check what will be the probability of the particle to be found in the region x equal to 0 to x equal to plus infinity. That is, this is equal to integral 0 to infinity probability density, that is mod psi square dx, that is equal to integral 0 to infinity mod psi square is d into e raised to minus 2k2x into dx. Now we can evaluate this function, that is we get probability is equal to d into e raised to minus 2k2x by minus 2k. So the limit is 0 to infinity, and when you are substituting these limits, you will get a finite value, that is it is not equal to 0. That is, the probability of finding the particle in the region 0 to infinity is not equal to 0. That means the particle can access that region also. But here you see the energy of the particle is less than potential barrier. Then how it can access the region from x equal to 0 to x equal to infinity? The reason is the particle is making a tunnel. That is, this is the barrier, right? So particle is here, this is the potential of the barrier, and the particle is here, or maybe you are here. Okay, so how you can access the region x equal to 0 to x equal to plus infinity? The one chance is you have to jump over this potential barrier. So in order to do that, you should have a sufficient energy, but your energy is this much only, that is E is less than V. Then what is the way of accessing the other region? The region is you have to make a tunnel. Many prisoners do this method. They make a tunnel in the prison wall and the access to the other region. Okay, so they can access here. So this is what the particle also doing. Particle is making a quantum tunnel and it reaches to the inaccessible region. That is in the region x equal to 0 to x equal to infinity. And this one is very interesting thing, right? So for the x value is greater than 0, in that region we got a probability density that is d square e raised to minus 2k2x. So there is a finite probability for finding the particle in the x greater than 0 region. Therefore, if the width of the wall is finite, that means like this one, some 0 to some x value. So this x is the length of this wall. Okay, and this potential barrier has certain height, that is V, and the energy of the particle is E, which is less than the potential barrier. Now there will be a incident wave and there will be a reflected wave. And the region x greater than 0, we got a wave function which is exponentially decreasing. Okay, so there is a probability of finding a traveling wave in the region where x is greater than 0 if width of the wall is finite. And if the amplitude of the wave at position x is 1 by e times the initial value, then we can find out the x value. How? That is, we know d square e raised to minus 2k2x will be equal to 1 by e times the d square, where d square is the amplitude of the wave when x value equal to 0. That is, here this is the amplitude of the wave, and we have to know the width of this potential barrier when the amplitude become 1 by e times, and that information we can extract from this equation. Okay, so we can cancel this d square and d square. E raised to minus 2k2x is equal to e raised to minus 1. Therefore, the x value is equal to 1 by 2k2. And we know what is the value of k2? K2 is equal to root of 2m v minus e by h cross square. We substituted, are you remembering, we substituted this value in the Schrodinger equation to solve the wave functions. So when x equal to 1 by 2k2, the amplitude of this wave will decrease to 1 by e times its amplitude at x equal to 0.